I think we can start. Bowei, thanks for joining, Bowei. Basically, Bowei is the head of infrastructure at Imbue. Maybe you can introduce yourself, and then we can kick it off from there.
Sure. Yeah. I'm so glad to have you to be here today with you, Aleksa, and your server. So I'm head of infra at Imbue. We are a pretty small AI startup. We're based in San Francisco, in California, in the United States. And I'm here to talk to you today about something which you ML folks may or may not have experience working with, but more of the hardware and the bare metal and the infrastructure and what goes on underneath the training that happens on these GPUs.
Hey guys, I want to give a huge shout out to Hyperstack folks who have generously sponsored my compute over the past month or so. Basically, I got 16 H100s, which is 2 8 GPU nodes, and the performance has been amazing, basically 2x the speed up compared to my A100 nodes. So I want to quickly show you how you can get started yourself. It takes basically 3 steps only. You go to the environments here, you create a new environment, you give it a name, you pick between Canada and Norway. That's the first step. The second step, you go to SSH keys here, you create a new pair, you pick environment you just created, you give it a name, you paste your public SSH key. That's it. And finally, go to virtual machines, deploy new machine, give it a name again, select environment. Let's select Canada here because they have more compute there. Then you select the hardware you want, like for example H100s. You select the images, you select the SSH key you just created, and hit deploy. That's it. Literally a couple of minutes to get started. It was really easy for me to just basically create these 2 nodes I just mentioned and get started running LLM trainings. So the documentation is super cool. I could actually solve all of my problems just by looking at their docs. They additionally have a Slack channel where they were super helpful, so I can't recommend them enough, honestly. The thing they kind of focus on is basically, because a lot of these GPU providers focus on big enterprises, so oftentimes you can't get on-demand H100s, whereas NextGen focuses particularly on that. You can get top-of-the-line hardware on demand, even if you're an individual or like a smaller team or whatnot. They also focus on bigger companies, but that's kind of their edge here. So without further ado, guys, let's go back to the talk. I do suggest you check them out, and let's continue.
Bowei, before we go there, let's maybe just quickly walk through your journey, how you ended up at Imbue, given that some people here will care about landing a job, but maybe even Imbue or something. So maybe if you can share a bit more about how you ended up there.
Yeah, super happy to. So I actually come from more of like a full stack SWE standard software engineer background. Imbue is my 5th startup. I was previously, so my first job that I joined out of university was a ML AI startup. It's called the Hive.ai. I believe it's still around. But yeah, I was doing ML AI infra there. And then after that, I actually went off and did non-AI infra stuff. So I was at 3 other startups, all pretty small, in the range of between 10 and 100 people. And then Imbue is my 5th startup now. So I joined roughly a year ago. I've been doing infrastructure here for around a year, mostly, honestly, setting up the infrastructure needed for our 70B model. And yeah, my educational background before that is I actually studied pure math at university, and
nice.
I was on a PhD track actually before I dropped out to do startups and ML AI stuff.
Nice. How did you decide when you're doing a PhD? How do you decide, like, obviously there are some tested names in the industry, like if you want to join OpenAI or DeepMind or Google or whatnot, Deep Tech, those are kind of like battle tested, so to speak. So how do you decide your first startup when you're doing PhD in math? Was it mostly somebody you knew basically recommended you, hey, come here, or was it more proactive on your side?
Yeah. So your question was, how do you decide when you're doing a PhD or when you're doing in research, how do you decide what companies to apply and what companies you should accept? So at the time I was doing research, but not in something like completely unrelated to ML. Like I was in the math partial differential equation space. But I had done some like math competitions. So I did have a friend who sort of introduced me into startups and software in general. And I had done like a little programming in classes before, so I came on at a very junior position at a place that wasn't even I guess doing ML AI at the time. But what really struck me about them is they worked with like data at a pretty large scale, which really positioned them well to make the transition into AI. This was back in like 2015, where like image CNNs were like first coming online. You know, like AlexNet is the paper that they sort of based their initial model architecture off of and stuff.
Nice, long time ago.
Yeah, ancient history now for some of these folks. Yeah.
So maybe walk me quickly through the decision to go to startups as opposed to just big tech. How did you think back then, if you remember?
I honestly, it was I was pretty young, pretty naive in the industry. Like I wasn't really sure of like how to get myself into some of these bigger tech roles. Like I was going to like career fairs and stuff, but I was coming from sort of a non-traditional background. So what I found is like startups really value different things from like big tech, who look more closely at like resumes and GPA and stuff, and like relevant internships and coursework. I essentially like went on site to interview with the startup, what was then called another name, but it's now Hive. I talked to the founder, and I think the founder gave me like a really impressive like startup energy kind of vibe, where it's just like, yeah, we want to work hard, we want to learn. The founder himself was like really young and like was trying to figure out what direction best to steer his company. So I sort of joined off vibes pretty much.
Nice. Okay. That's a solid heuristic as well. Just go on vibes. My heuristic for enrolling into electrical engineering is I'm looking for what's the hardest thing in my country, and I'm like, okay, electrical engineering was considered one of the hardest things to do, and then I just kind of went that way. It's not always the best heuristic, but it worked out for me. Having said that, I think unless people in the audience have some questions, we can continue. And by the way, like if you have questions, raise a hand, and then I'll just let you speak so we can curate it.
Mm-hmm.
So, okay. Awesome. You can kick it off, Bowei.
Oh yeah, I'll just continue. Yeah, again, like, yeah, please interrupt. I also have a habit, because I used to be a grad student, of like restating questions that get asked to me, just to make sure that I understand what's being asked, and so that other people can hear them as well. So I'll probably be doing that throughout this talk. Anyway, that's a little bit about me. I can also talk a little bit more about why I joined Imbue. Oh, is that oh, sorry. Yeah, please interrupt me if it's a question. If it's just a comment, you guys can chat amongst yourselves in the the Google Meet chat as well.
Ignore the chat. Feel free to ignore the chat. And yes, tell us more about Imbue.
Yeah. So prior to this, I was actually at a full stack startup doing a mixture of web development and backend. We were building a collaborative whiteboard for engineers. And while I was there, I was like thinking more like long term, like what do I want to do with my career? Where do I see myself in engineering? And based on one of my previous roles, I had interacted heavily with one of the infrastructure engineers there, and the infrastructure manager. And that team just struck me especially as just having really deep knowledge and the ability to debug any problem, right? So you're doing some ML training, or you're like looking into your web server and it goes down or something, and then you're like, why is this happening? You know, like what docs can I look for these errors? And sometimes you are able to debug yourself, but sometimes when you're out of ideas, you have to go down further in the stack, go down in the kernel level, and even the hardware level. Sometimes like poke through the cloud abstractions. And so infrastructure in general struck me as the folks who know how to get those answers. And that's one reason why I started looking for an infra role. And it just so happens that Imbue, around 1 year before, had just raised a Series B around 200 million USD from various, I guess, venture capital folks. And they were interested in scaling up, getting on board with training larger models and building out, owning their own hardware infrastructure to do this. So it was actually a really great timing for me, because I just started exploring infra roles, reaching out some contacts in my network is how I heard about Imbue. And it was also a good opportunity for me because, again, this was around a year ago, maybe around a year before that, like ChatGPT, generative LLMs were super hype back then. So I was like, yeah, seems like a good fit. And the interview process really convinced me that Imbue was where I wanted to work for a longer time. I really appreciate like how thoughtful the interview process is here. For instance, one thing we do that's fairly unique that I haven't seen in a lot of other places, we have candidates come on site to our San Francisco office for between 1 to 2 days. And that way they can actually integrate with the team and figure out what it's like working day to day with the CEO, the CTO, and the rest of the technology stack. Which is something that I personally, always wondered when I'm interviewing at startups. It's like I'm doing all these like coding questions, and I'm like, you're doing some architecture design, but what do you folks actually do day to day? Is what I was wondering. So I feel like Imbue's interview process really answered that for me.
Nice. And when you say you fly out the candidates, does that mean somebody who's already in the Bay Area, or would you like fly out somebody from Asia or Europe? I guess.
Oh yeah. Yeah, we've flown out people from the UK, for instance, or east coast of the United States, or other places as well.
Nice.
Yeah, and we do try to we do understand that there's like a time zone difference, so we try to give them like a day or so before to just adjust and get some sleep if they hadn't slept on the plane. Yeah,
Awesome.
but I really like here. It's again we're around 30 headcount right now in Imbue. So it's definitely startup vibes. Like there's definitely like a wide scale of AI startups, and like one of the examples here is like we don't really have titles. Like everyone here is technically like member of technical staff, so I get to make up whatever title I want, including head of infra.
Nice.
Yeah.
Awesome. Thanks for sharing the context there.
Yeah, and then I had some people actually help me with these slides. So here's a little more data about Imbue. This is our pitch. You can also find this on our website, imbue.com. We are interested in building AI that can build software, essentially. We recently finished training a 70B model from scratch. So that's mostly what I'm gonna center this talk around, but I'm also open to getting distracted and talking about tangents.
Mm-hmm. That's why I got to first hear about your work. I mean, I knew about Imbue back in Neurips. I actually met with your founder at Neurips 2022 or something. Back then, I don't think you raised 200 million back then, but I think you probably pivoted since then, because back then you were trying to be an AGI lab. Like nowadays, I don't know you're probably not trying to compete with OpenAI in the world.
Yeah,
but super cool.
Yeah. I would say we've definitely pivoted since then. You're right. I think one of the charms of being at a small startup is being flexible and lean and open to listening to what the market is telling us. For instance, I think maybe even around a year ago, people were like honestly a little scared of AGI. Like people were like, oh, we're building too fast. Like, oh, we're going to get there too soon. There's going to be a singularity. But nowadays, I feel like people have sort of settled, the industry in general maybe has settled into the idea that these generative LLMs, they offer solutions, but there are also a lot of problems with them. Like one of the problems we're focusing on is reasoning and the ability to verify just accurately what the code that's generated is correct or not. And it seems like there's still a lot of research to do on that end before we can say like, oh, these AIs are like ready to take over the world and all they need is more GPUs. Okay. And then I understand there's a decent number of you folks who are in the audience who are researchers. So I do want to say I asked a researcher to give me the pitch on this like just yesterday. So one of the reasons why I think the researchers who do have are really happy here are it's a small team. There's lots of opportunities to contribute, and there's just a lot of opportunities to discuss ideas amongst the team. One thing we do every week is we have a weekly reading party. So we'll pick a paper that's we think is probably relevant to our interests, and we'll read it together and sort of discuss and see what ideas there can be actually folded into our day-to-day next week or next month or something. In terms of hiring, I would say we're really interested in people who can be mostly self-sufficient. I think we don't really have the bandwidth to take on, interns or that many like fresh researchers who are still finding their feet in the field. But of course, we're willing to make exceptions, and we're definitely interested in people who are a little more experienced on the research side, not necessarily with like we don't require that you come with like a lot of ideas or like a lot of theory. We're mostly interested in like, can you run and replicate experiments? Can you make significant progress day to day? and just help out the team and pair with maybe other researchers and make some progress on our research directions. And so, like I said before, we are particularly interested in the verification process. So given an LLM that generates a snippet of code, how can we train an LLM to be better at distinguishing a good generation from bad generation? And like, what is the process for even defining the good and bad generations? You know, can we fold these into unit tests? Can we fold these into, can we give the LLM some runtime information? Stuff like this is all within scope. And one of the other research directions we're interested in is adding more like chain of thought reasoning traces to generations. And the hope there is, the hope with both of these directions actually is that regardless of what large foundation model, open source, like Llama 3, ChatGPT equivalent that comes out in the next year or so, we're hoping that these layers can continue to be useful on top of whatever baseline or foundation. And we're also obviously willing to fine tune as well on top of these.
Nice. I gotta say, I'm surprised that you're not exploiting interns more. Like most companies, there's just cheap labor for you there. graduate student descent, as I think Karpati said, or somebody. Yeah.
Yeah, I would say like it's more to do with like our management structure and our culture. We don't really think of like work at Imbue as being like very top down. Like you get told what to do and you have to like grind it out and ship. We really want like everyone to feel responsible for the work they do and the work that other people in their immediate vicinity are contributing towards, and have more ownership of like company direction, and be able to make more of their own decisions around like, as long as like we're aligned, you know, on a high level with the CEO, the CTO, the rest of the research team, like you can have a lot of say in like what specific things you think are most viable.
Maybe a quick question: how focused are you on actual products versus research? If you can maybe share about that.
So I would say it's changed recently. Actually, we used to be. Like as you can see, like we used to be very focused on training this big foundation model and doing research there. I think recently we've felt the need for more accurate or more realistic training data to deliver a sort of like good product experience. So basically in the last quarter we've scaled up more of the product side. So that also means there's more roles open for generic SWE backend, and like I would say like a sort of a mixture between research and product, like doing some small scale experiments and stuff like this on the product side. So you just summarize. You're asking like how is our split between product and research? I would say even on I would say we are maybe a little more on the product side, but even on the product side, we're still like at our roots, I think, a research lab, and we're doing a lot of research and product prototyping on that side as well. Hope that answers your question.
Yep, thanks.
Okay. Yeah, I can talk a little bit about the 70B model that we trained. So we pre-trained this from scratch. We grabbed our own data sets as well. So we mostly use the open source data sets, but we also had some proprietary eval data, which we use to tune hyperparameters. And then we also have tuned our own split and cleaning algorithms for the like large corpuses of data that we trained on. So there are posts on both of those on our website, imbue.com. I will skip a slide. I think people might want to know just like what actually goes into the 70B model. So I also got this from someone else, because this actually predates my time at Imbue. We were training 7B models before I joined to get us all scaled up onto the large cluster. But at the time, we were based on standard architectures like following Llama 3. We have fast attention in there as well. And then on top of that, we had a few tweaks to the tokenizer. Obviously, the hyperparameter search sweep we use called Carbs. We developed in-house, and we have a paper on that. And then we also have some CUDA kernel acceleration code that was put in at some point. I would say most of the code in our code base, actually on the training side, is just scaffolding to get all of this stuff running and debuggable and effectively scaled on multi-GPU. For instance, like around Torch Run, we have our own wrapper, which we just use to inject debug information and also just set all the environment variables correctly that we need to debug on the NCCL side. And then surrounding all, yeah, go on.
Quick question. You mentioned CUDA kernels. Like, do you have in-house CUDA experts, or is it mostly, hey, I picked it up because we don't have anybody who's dedicated to this role and I wanted to learn it? Like, how do you think about
it's much more the latter. Like, I think we don't even have a lot of expertise on the CUDA kernel side. We've just read, some blog posts that are like, okay, you guys should. It's good practice to profile like which kernels are being slow, and then we noticed that like I think one or two particular kernels are slow, and then one person on our team was like, oh, I really want to like figure out how this works and see if I can improve it. There seems to be a lot of upside here, and after that, he spent I don't know, like maybe 1 to 2 weeks like figuring out how to get the how to insert the correct code there.
How do you think about hiring for those roles? Would you even consider having a dedicated person who is doing just low-level stuff? Or I'm just thinking out loud, like what's the scale of a startup where you can justify having such experts? I guess it depends on how much money they can save you, I guess.
Yeah, that's definitely a big factor. We would probably want, before we make a decision, we'd probably want to do some profiling and see like what do we have a good estimate on what we think the potential upside is of doing that optimization. And then in terms of like hiring someone who specifically has that expertise, I think our general mode of hiring here is we want people to be like broadly capable and also have like rather narrow specialties. So if someone has like a lot of experience in CUDA kernels, we would still want them to be, like quite competent at other research tasks in case there's not a lot of CUDA kernel to write, or in case we write one and it's like, oh, it's really amazing. It speeds up everything. That's that's exactly what we needed. And then we would want them to go shift onto other tasks like more of the debugging or scaffolding or research allocation scheduling type code as well.
Mm-hmm. And related question, where do you find people? How do you think about hiring right now? Like, do you look like at the GitHub profiles, or like see who is contributing in the open source community, or you use some websites, or what's the flow for you?
Yeah, we have a recruiting team. We can probably talk more about this. But we do a lot of sourcing from our contacts in the research community. So we have some graduates from Stanford and various other labs that we reach out to their connections to. We obviously also try to keep track of promising fresh grads or promising research. For instance, like you mentioned, you met Kenjin and NeurIPS probably. I believe we went to NeurIPS last year as well, and sort of send feelers out in the community and try to figure out who's good and who's working on relevant stuff, and most importantly, who's just interested in joining like a small, more scrappy startup like us and exploring what we want to explore. And then I was going off here. One other charm I'm working in a few is we have an internal job scheduler for allocating GPU compute resources. It's not Slurm, which obviously is very popular in the community. It's not Kubernetes, which is, I feel like, the other big player in the scheduler space. But I'm very happy with it. It was built internally. It's built mainly, honestly, just using Python code that hooks into OS calls, hooks into our Docker containers, and hooks into SSH. And it doesn't handle any logs. We have a separate log aggregation system for that. That's the standard Prometheus Grafana setup. But yeah, I don't know. I've personally actually worked both with Slurm and Kubernetes, and I would say our system is better day to day. It's more optimized for solving the problems we want to solve.
How many tokens? Maybe talking about 70B model. Like, how many tokens did you use? And also, because you were training from scratch, did you experiment with MIUP?
Yeah, so I can talk about both of those. So you asked about token count and MIUP. So I believe it was 200 trillion tokens. And the way we actually determined the correct token count and also which data mixes to go into tokens is through the hyperparameter optimizer and using the chinchilla scaling laws. So we trained a bunch of smaller models first, and we have a system that runs like small models in parallel, one per server, and also like medium-sized models using InfiniBand, like multi GPU, multi-server, like medium-sized models, and we also train a bunch of these in parallel. So using that, we were able to find what is the correct token size relative to the actual amount of money we're spending on this compute. And then you also asked about MuP. Yeah, so I think midway through training the 70, the large 3-month training run, we started looking into MuP as preparation for maybe a subsequent training run that we wanted to do. I think we got that merged into the code base, but we didn't have a chance to like run the hyperparameter scaling and actually test this at scale. Also, I was not like particularly involved in the MuP optimization, so I don't know too much about it. But yeah, it's definitely something we looked into. Yeah, thanks for asking.
No worries.
Yeah,
no worries. Yeah, I guess the number of tokens was probably 200 billion, not trillion.
Oh, sorry. Yeah, sorry.
No
Apologies.
worries.
Yeah. Okay, and then hopefully I get to talk about the stuff I'm excited about, which is like the hardware that compute. So this is 511 hosts. That's around 4,000 GPUs, H100s. These are located in the northwestern United States, so pretty close to us since we're on the West Coast. Means good latency. This is a long-term rental. I can speak a little more about our motivations here as well. So this was back right when H100s were coming online, and we noticed that there were a lot of supply issues. So we worked really closely with one of our partners called Vulture Park to basically secure a long-term contract for them. And so because they were also building multiple data centers at the time, they were able to use this like scale and build out to essentially like jump the queue in terms of NVIDIA and getting early access to these H100s. So I believe we were definitely not like first to get these H100s online, but I think we were the first to get these H100s online in the specific like server chassis that we use. And this process started, I would say, like August 2023, and it's been ongoing. I think we got a final delivery somewhere around October, and we've been fixing issues and like learning how to service InfiniBand cluster of this size, just like all in-house. So that's definitely been a huge learning experience for us, and that's what I'm most excited to talk about here on this talk today. But yeah, I think I would say we got like actual training running smoothly without like just tremendous amounts of downtime. I would say like we got around 90% uptime somewhere around February, March of training the large model. We basically couldn't start effectively training before then. And yeah, around I think May or June, we like sort of wrapped this up, and we took the time to like clean up all the scripts and release and write up the training process, as well as open source some of these scripts. So if you guys feel interested, you guys can actually go to our blog post, and there's a GitHub link, and you can see what goes into all the setup scripts. Yeah. So again, I don't know how much background y'all have on the infrastructure side of like what it takes to set up one of these clusters. So please stop me if I'm using like unfamiliar acronyms or things that could use a little more explanation. But this is yeah.
Go ahead. There is no way somebody will not understand something. We can always Google stuff and
yeah. That's right.
Yeah. So just go ahead.
Yeah, this is a huge learning process for us as well. So we got access to these hosts as bare metal hosts. So we don't have just short of like physical access to the data center, which we don't have, but we have a relationship with a company that does do that. We have access to the management consoles on all these devices, and that's sort of it, right? They didn't actually ship with any OSs. They shipped with like SSDs and drives, but we also had to set those up. So I'm going to talk about those. So this is just our hardware spec. We have the 4800s. We have pretty beefy CPUs and 1 terabyte of RAM per machine in there as well, and like 10 terabytes of disk space. These are all also networked using InfiniBand. And InfiniBand is the technology that allows really fast direct GPU to GPU communication. So since these GPUs send so much data, it's not efficient for the 8 GPUs all to send data up to the CPU and then to go out through one Ethernet connection. Instead, each GPU has its own 400 gigabit dedicated cable that goes up into a switch. All these 4,000 GPUs then are networked together in the InfiniBand network architecture. And that's a separate network from the Ethernet. The Ethernet is what we use to like SSH and pass around the training data and stuff. So here's an overview of the different tiers of the InfiniBand topology, actually. So we were given this in like a table format of like basically you can think of it as an incidence graph. You have one node on a switch and one node on this other switch, and you have a table of which connections go where. And so we had to work out a high-level understanding of the topology here. So that was definitely a learning experience for us as well.
Quick question here: like, how much of this network topology is just like off the shelf? So did you have to kind of think through multiple design options and then pick one, or did you have to do it completely custom, or like, can you maybe walk us through? I'm not familiar with.
So the overall design was given to us, and then we just had to like essentially verify it and make sure that the cabling on the ground actually matches the design, which is something that we did write a small script for. But this is a pretty standard topology. It's recommended by NVIDIA. The one in particular we use is rail optimized fat tree. That's just what it's called, rail optimized fat tree, which means that in a block of 32 hosts, that is 256 GPUs, all of the GPUs at index 0 are connected together, and then directly to the upstream leaf switch. And similarly, in the block of 32 hosts, the 32 GPUs at index 1 are all connected together. And we call each of these indexes a rail. So GPU 0 is on all the hosts is like rail 0. And this makes it so that all the GPUs at rail 0 can communicate to each other at lower latency because there's one fewer hop in the network than like GPU 0 on one host connected to GPU like 5 on the same host. And one of the reasons the network is designed like this is because there's this technology on the hosts called NVLink, which ensures that it's basically another path for the data. So if the data on GPU 0 on the same host, on one host wants to go to GPU 5 on a different host, it has sort of two choices. It can go through the full InfiniBand network, so all the way up to tier 4 at the top of the tree, or it can go on the same machine to GPU 0, and then it can go sort of a shortcut and only go like one step up in the tree and one step down.
How are those routing decisions made? Like which software is part of the stack handles picking those optimal decisions?
So you asked what part of the software handles the routing and how to determine like if one GPU wants to send data to another, like how does it actually get through the network? So we actually, NVIDIA has provisioned us the standard software here, which is called UFM, Unified Fabric Manager. This is, we have one dedicated non-GPU server that runs this software. It talks via InfiniBand, like to the management interfaces on all these InfiniBand switches. And each of these InfiniBand switches has like a little routing algorithm that says like, oh, I've received one data packet from this GPU dedicated for this other GPU. Like, how do I know where to send it? And the GPUs themselves also, as I understand it, there is some knowledge in the NCCL, the nickel all-reduce algorithms that are aware of this topology and try to make the similar rail GPUs talk to each other slightly more.
Got it. So unless you're literally very, very low level at the nickel level, lower, you don't really care about, you're abstracting away the hardware completely. Is that fair to
absolutely.
Say? Okay.
Yeah. So this is why like a lot of ML researchers like don't really see this day to day. They just train on even on top of nickel, right? So the CUDA drivers all call into the nickel bindings, I believe. So when you're spinning up a training run, you don't see any of this, like all of this abstracted. But like physically, this data has to go through these wires at some point. and it actually matters very much to us, like which of the wires, if there's any failures, where they are in the network. Because at the lower level, each GPU is actually there's no redundancy. There is a redundancy in that like it can go to another GPU on the same host, but the link from each GPU up to the leaf switch is actually unique. So if that cable fails, we can tell pretty fast. Like it's going to result in a fairly obvious degradation because the other 7 links essentially don't have enough bandwidth a lot of the time for the type of training that you want to do when you're training a 70B, as opposed to like the links in between T2 and T3 or T3 and T4. Those are optimized for throughput, but a lot of those are parallel links. So if one of them goes down, it's detrimental to the network in the sense that like the routers have to figure out like basically remap the network and reroute stuff around it, and which will incur latency costs. But it's a lot less harmful to like the overall bandwidth of say one specific machine. And then I can also talk about what this looks like in training, which is maybe something like there's the InfiniBand guys at the low level who will tell you like, oh, this cable is downed, or this link is flapping. Flapping just means it's sometimes up and sometimes down, and it depends on when you look at it. And then there's like the ML researchers who care about their training benchmarks, like how much seconds per step, what is the MFU, model flops utilization, what's the GPU utilization. And we're actually a small team, so we have a lot of interconnect between the people who are in charge of both. And so I in particular can speak to like what if a link goes down? Like how can you tell just from like MFU shape? So one thing that has happened to us quite a few times is we'll kick off the training, and then there's like the 5-minute startup time where it initializes the weights on all the GPUs. And you start negotiating the nickel initialization. But what will actually happen is it'll randomly train, and then randomly the NCCL will hang, and you'll just be like, oh, it's not doing any training. It's stuck in one of the training steps in the backwards pass, for instance. And if you go fetch out the debug information of like in the NCCL debug of like what it's doing, you're just like it's been waiting. One of the GPUs is waiting to receive data from the other GPU, but the other GPU claims it's already sent it, and this sort of data is lost in the network. And it may be like a fairly large tensor. So you're like, can you tell me like which exact bit of the tensor was lost? And it's just like, no. It just decides to like hang for like 5 minutes, and then it'll in fact continue hanging generally until it hits the NCCL timeout. And this will crash your run, and you'll have a CUDA error, and this will trickle up to torch, and you're like, how do I debug this? And generally, the answer actually is you have to look at the InfiniBand fabric and be like, which link went down at the wrong time that caused one of the data packets to get dropped. The NCCL version that you're using probably has no recovery method for this synchronized all reduce, just one of the tensors getting like falling out of the network. So this was a pretty big pain point for us in the training. This was not the first pain point that we had working with the InfiniBand network, but this is definitely one of the ones that was most painful later on in the training process.
Mm-hmm. Why do you think the timers are set by default to like a crazy big number, like 30 minutes?
Oh
like, did you ever observe the situation where like a packet arrived 29 minutes after the
Okay. No. So I think one thing that people do is in some instantiations of the training loop, they'll do an NCCL all reduce, and then in the middle of that there'll be an upload of like your weights. Like because you're on step 200, you're like, okay, I want to save a checkpoint. I'll save that checkpoint up. And my understanding is like there's some training frameworks who that try to do that in the middle of the NCCL packet. So that's one reason why it's actually important to not set the NCCL timeout too low. It's because if you have a bad Ethernet network uplink and you try to upload your checkpoint to S3 and you have a very high like NCCL parallelism, so that like you're essentially trying to do another forward step or backward step while you're trying to upload checkpoints, the one or a couple machines which are responsible for uploading the checkpoint will actually slow down the rest of the NCCL group that it's in, and you'll hit up against NCCL timeout on that regard. Like it's going to be timing out the the specific op that it's doing, like the low-level NCCL op, regardless of like what's causing the slowdown, whether it's something on the hardware or something you're doing on the software stack.
That makes sense. It's just that
Yeah.
you have like a machine that costs many millions of dollars waiting for like a cheap Ethereum uplink to upload. So like I still think you should probably fix the uplink and not like increase the timeout, like just
yeah. So one of the first things we did, for instance, is we have like these 500 hosts, right? So obviously when we save weights, we want to the weights are sharded. So we save we tell each individual server to save all its weights. But one thing we do is we try to save those locally to the local disk first, and then have an async process in Python, basically on another thread that's able to pick these up and send these up to like shared storage or to AWS S3 or whatever you need it. Definitely prefer shared storage inside the data center, as that's going to be significantly faster in terms of Ethernet bandwidth compared to sharing up to S3, because just due to the nature of our cluster, the 100 gigabit link we have to the public internet is it's like shared amongst all the nodes in the data center. So whether you have one node trying to like max out the S3 upload, or you have like 500 nodes all trying to mash as much data as you can through the pipe. Like the pipe is only so big, you're not gonna have a good time. But like these are all details that that matter when you're training a network of this size, and they also matter depending on your specific hardware deployment. Like maybe you'll be working somewhere else at another company, and they have like a really good Ethernet uplink, but they don't have as good bandwidth on the local storage, or maybe the local storage has good bandwidth, but there's a relatively high latency cost there, and then the latency then runs up against whatever Python S3 library you're using. So it benefits a lot from knowing exactly where in the stack and what hardware components are being the bottlenecks.
Mm-hmm. There is one question from Suraj.
Yes.
He's curious if there is any specific reasons to write your own scheduler instead of using subset of features from either Slurm or a lightweight Kubernetes.
Yeah. So the question is why didn't we pick the good parts of Slurm and Kubernetes rather than writing our own? I think this was a decision that honestly predated me a little, but one upside that I can see of working with our own system is that we can tune it to do specific things that we want, that are relevant to our cluster and how we want to use it. For instance, one thing that we do is because we use Docker images, and we don't want to pull all these down through the 100 gigabit pipe that we have out to the public internet. So we integrate with a software called Kraken, Kraken, from GitHub, just written by Uber. It's an open source software. It essentially uses a BitTorrent-like interface to share the exact same Docker image across the entire network. And it was relatively easy for us to integrate this into our scheduler and have it so that like when you schedule a new job, when you build your new image that you just fix the bug in and try to push it up, and then want to push it down on all these 500 hosts, it's as fast as possible. And this ensures a quick development cycle. And it's something obviously that's possible in Slurm or Kubernetes, but we just feel that like based on the fact that we wrote the scheduler and we're more familiar with it, this is easier to do on our end. Okay, yeah. So going back to like how this started up, so one of the things that happened with the cluster is we received these in chunks of 128. So the first thing that we do after we get access to the management consoles is we provision the OS on them. We use a software called Mask. It's open source by Ubuntu. It's called Ubuntu Metal as a Service. We connect to the management controller. We boot these over Pixie Boot. So essentially, we send the OS image over the Ethernet network out to all these machines. We give them IP addresses via DHCP, the IP discovery protocol, and we try to boot them into the OS. So yeah, so at the beginning, there were a lot of boxes that just failed to boot up. This was just due to hardware issues. Like these boxes have to be physically shipped from somewhere, and they have to be physically installed. And there's a certain failure rate that happens, like when you plug in all the cables and power it on for the first time. These machines have like a lot of internal components that are relatively susceptible to like jostling, whether they're in like the USBX truck or when they're getting lifted up into the server rack that they're getting slotted into. So our first step was just to diagnose all the broken machines from the hardware perspective and make sure the OS is flashed onto them, make sure the essential NVIDIA driver, Mellanox driver, InfiniBand stack, software stack is all installed on there. And then at that point, these nodes will be ready for a single node GPU training. And that is what we used them for in the beginning before we validated the InfiniBand fabric was working. So this would be like running individual like dev notebooks, Jupyter notebooks, or obviously we don't have that many, but also running some small experiments in hyperparameter tuning, stuff like that. I guess I'm actually going to skip through most of my slides and try to talk more about some of the experiences we had setting these up.
I think that's great. And by the way, can you share the slides after the meeting?
Oh yeah, yeah.
Somebody asked already in the chat. Cool.
Yeah, so most of the slides in the middle were honestly taken from our infrastructure write-up, which is actually just available on our blog. So I want to keep this keep you guys available, get you guys more insider info here. So yeah, one of like in the very early days, we're like, why do these boxes have so much hardware issues now? And what we found out is like first that this is like kind of standard for GPU deployments of this scale. Like this is new hardware. These like the design and infrastructure of the server boxes themselves is like non-trivial. And so we got on calls with basically everyone that we're involved with, so Dell and NVIDIA Voltage Park, and the folks that are physically on hands in our data center to try to understand more about which components are most likely to fail, or which components that are more important to check more often and can fail by themselves, as opposed to like that fail have more likely to fail just only on power cycles. One of the other things that we invented back when we were provisioning the OS that we're still doing to this day is actually so there's this command on the Linux Ubuntu service called dmessage. It's here. It basically, when the server first boots up, it takes diagnostics of like every single like booting operation, kernel operation, setup operation that happens, like each piece of hardware like that gets any sort of diagnostics around boot. These all show up in dmessage. And what we did is, because we expect all of these machines to be exact same, we sort of know what are the allowed dmessage like errors and warnings, because there's obviously a lot of errors and warnings in there that are like not particularly relevant to our training. So we went through and cataloged like each and every one of these boot messages, and we're like, okay, has this one been seen before? Yes. Has it during a good training run? Yes. Okay, then we can ignore it. Right? And if anything new shows up, we're like, oh, something showed up there on this machine. We don't expect that. Let's look into this machine a little bit more and see if we can run some extra diagnostics, because it's doing something it shouldn't. And this is also just extremely specific. Like I think this is maybe one of our health checks that we either shared publicly or didn't. Maybe we didn't share it publicly, or maybe we did, but it doesn't really work well. And it's because like it interfaces with every single piece of hardware you have in your stack. So if you have like slightly different hardware from a slightly different manufacturer, it's not going to match up against the specific allow list that we built. So this is something that you guys, you folks, would probably want to like rebuild if you care. If this is an issue that you run into again. I talked about custom stack. Yeah. I'm going to go back over to the overview. Where is the overview? Yeah, so after OS installation, after we root out all the dmessage hardware issues, the InfiniBand cluster, the fabric health is the next thing we check. So we also learned this via just talking, learning about the InfiniBand technology from talking with the NVIDIA folks. There's a couple low-level tests that we always run first that are basically like bandwidth and latency tests on each of the cables. So this is something we used to do at the beginning manually. We're like, okay, this box is looking sort of funny. It has 8 InfiniBand links. Let's just use like essentially like an internet speed test, but configured over the InfiniBand cables to make sure that each of the cables is operating at the expected speeds. And we're like, okay, yeah, they're all running at like 400 gigabits per second or whatnot. And if that's true, that's good. And if not, then there's an issue. But there's, it's honestly a little bit of an art deciding like when is too low, because these cables are rated for 400 gigabits. Generally in production, they're not expected to run at the full 400 gigabits, and especially during training, like it's not always required to run these at maximum. So we're pretty happy with honestly anything above like 360 gigabits, and sometimes even lower than that is fine. Like somewhere in the vicinity of like 300 gigabits is not ideal, but if it only happens like once in a while, maybe it's just attributed to like, I don't know, maybe one of the switch on the other end is like a little busy or not as responsive as we would like. And yeah, so it's like we've had to go through like a variety of thresholds. If we set the threshold too high, it'll have false positives, and we're like, hello, like we're literally using this node in training. It just came out of a good training run that we have good MFU and numbers for, and our tests are telling it that the infinite bandwidth is too low and it should be taken down. Like that's not ideal. We're going to run out of nodes at that point if we keep taking out nodes like this. So definitely more of an art than a science there. What else? I would also like to talk about this the garbage collect related MFU group. This was probably the first issue that we ran into when we started scaling up from like small 7B models to a 30B model. So like the first run we saw this on was I believe like on 80 machines. We hadn't run a multi-machine InfiniBand run of that size yet. As we saw this really weird behavior where it would start off with a good performance, good step timers. Like each training step was going pretty fast, and then gradually over time it would degrade to around like 70. I can't draw, but it would just gradually degrade over time, and then we would have to like take it down and restart the training off the latest checkpoint, and then when we did that, it would magically go back up to like 100% of like what we expect to see on the MFU there. I'm like, why is this happening? Is it our first thought was obviously like something physical, like this smells like heat related. Like maybe the GPUs and the InfiniBand cables are getting too hot in the data center when we run, and that's what causes the performance degradation. And this is obviously pretty difficult to test. But one thing that really set us off and made us suspicious is that after a checkpoint, or after we like would save a checkpoint, that is when we would see the most like increased variance in how much the MFU was degrading. And every time we save a checkpoint, it would get slightly worse. But like in between checkpoint, it was like roughly constant, like basically how bad the droop was over time. And like what could be causing this? And we debugged all over the stack. Like we ran the Nsight profiler, we ran PySpy, Python, like thread spying to see where the Python was spending time. And eventually, one of our folks. And the other things we did was we took out real data. We thought like, is this a data loader issue? Like, is there some sort of bandwidth there based on like how fast it's fetching data out of the disk? So we disabled this guy. We made sure that the random seed in terms of data shuffling was entirely deterministic, and then we eventually nailed it down. Someone made the really astute observation that like it might be that these machines are like getting like slightly more and more out of sync with each other, because like we would do profiling on each individual machine, and we're like, oh, but each like one of the machines is being slow, but the next time around it's some other machine. Like this is really suspicious. And we eventually, someone like thought of like garbage collection. Like maybe it's the Python garbage collector that is causing like maybe one machine randomly decides to do garbage collection while the other machines are waiting for the NCCL to all reduce. So when that happens, like that guy will slow down. And as the run progresses, if you do something like checkpointing, which passes a lot of stuff through the Python memory, like there'll be a lot more opportunities for these things to do random garbage collection at random times and desync all the NCCL reduces gradually as the run goes on. So we put in custom environment variable to disable garbage collection and only do it when deterministically when we need to, and then that actually fixed the MFU droop, and we were just so happy when we figured that out. That was an incredible find.
That's a tricky one. There is one question from Suraj. Maybe you can read it as well if you want. It's a bit longer.
Oh yeah, sure. Infinibit incompatibility due to OS firmware Mellanox and drivers from different sources. Get a patch driver to continue. Yes. We did in the very beginning. So we had an issue with the latest NVIDIA driver that we started the training on, and we did have to go to NVIDIA support and ask them, like, why is this driver seems to be incompatible with on the other side of the stack? And like, yeah, they just told us, like, okay, yeah, that driver is just a little broken on your specific hardware stack. Either go up or go down. So we actually ended up going down, and we've been pinned on that driver version ever since. So maybe that's not what you want to hear, but that's just what's worked for us. And that goes to one of the points we raised in the blog post of, like, just change as little as possible at any given time. And like, if it doesn't work, but it works with one driver, just stay on the driver for as long as you can. Like, make sure you know the rest of the errors in your training stack, and then once you're confident that you're pretty experienced working with the source of errors, then you can try to upgrade your driver and see, and also be ready to roll back if necessary. We've also had that happen in other components in the firmware stack. Like there's like maybe a BIOS firmware that we need to upgrade, and we always make sure to do it on half of the cluster first, and then run some basic profiling, like essentially run a 70B training model for like 100 or so iterations. Make sure it's actually attaining the same training speed that we do on the other half of the cluster before we spend the time to upgrade the entire cluster up to the same version. And if it does not pass the test, we'll just roll that back down and notify our vendors, or just like look around for what on earth is going on with that incompatibility.
Are you even a serious infra engineer if you don't know the driver version when somebody wakes you up in the middle of the night? It's just those have to become your friends.
Yeah. Vendors will always tell you as well to upgrade their drivers to the most recent version, and I would just take that with a grain of salt. Sometimes they're not as reliable as they think they are, and it's up to you to basically verify that the most recent driver version actually fixes your problem and doesn't introduce other problems elsewhere in the stack.
I think we're out of time. Maybe if you have some interesting one from the last slide that you want to share, and we can slowly wrap it up.
Yeah, I guess this is maybe a little embarrassing, but something that has happened to us. We did get stuck for a week on two separate, unrelated configs that we just had hard-coded in the environment variables. Like, I think one time it was like CUDA-Max devices was not set properly, and another one we were just literally running off of the wrong architecture and trying to match up the MFU numbers against these two, like, obviously different configurations. But at the time we were like, what is going on? We're so confused. We didn't think to check. So this is one learning from us is try to make sure, like, all your runs are as reproducible as possible. We obviously pinned to the Git versions, but these two configs in particular were not being loaded from Git or being loaded from local flat files. So we lost an unfortunate week there, being very confused and thinking we were going crazy. And it's not us. It's just the configs. Just remember to check the configs.
Awesome. Bowei. By the way, am I butchering your name? Bowei or
yeah, Bowei. That's correct. Yeah.
Bowei. Awesome. Cool. Thanks for sharing the struggle. The struggle is real. Yeah, I guess most folks will never have to really build their own cluster. I did have my own share of dealing with some of these low-level details, and the LLMC framework that I've been working on with Andrei Karpathy and a couple of other folks, like the lowest we got was like nickel, so I never had to actually go below that and actually like install like OS on separate machines and do everything you guys had to do. So it was really interesting to read through the blog and also have you here on the server, I guess.
But yeah, thanks for having me, Aleksa. Yeah.